Welcome everyone to yet another episode of Talking Robotics. I'm delighted and we are all so happy to have Anushri with us today from Princeton. So Anushri is a postdoctoral researcher in the Department of Mechanical and Aerospace Engineering at Princeton University. She received her Ph.D. in Control and Dynamical Systems from Caltech in 2023. And her BS in Electrical Engineering from Georgia Tech in 2017. Her research focuses on motion planning and control of robots in unstructured environments while accounting for uncertainty in a principled manner. Her work on risk-aware methodologies for planning has been deployed on various robotic platforms as part of Team CoSTAR's effort in the DARPA Subterranean Challenge. She has received the Outstanding Student Paper Award at the Conference on Decision and Control, Best Student Paper Award at the Conference of Robot Learning, and was selected as a Rising Star in Data Science by the University of Chicago. She will start as an assistant professor at the University of California, Los Angeles in Mechanical and Aerospace Engineering in July 2024.
Thanks for the introduction, Ridwan. Hi, everyone. I'm Anushri. And today I want to talk about some of our work on safety assurances for vision-based navigation. This work is in collaboration with Zita May, Megan Booker, Mariko Story-Matsutani, Alan Wren, and Ani Majumdar. And we're all a part of IROM Lab at Princeton. So, modern learned perception systems are very powerful. You can see in this video that Tesla Autopilot is able to autonomously navigate in this suburban setting, and it's able to detect different objects in the environment. You can see it on the side. Cars to detect. But a lot of these systems are still not reliable. You can see here Tesla Autopilot actually is not able to safely avoid pedestrians due to perception failures. And this is kind of a test that this YouTube channel has done to check how well Autopilot works. But this happens in the real world as well. Cruise about late last year had to recall its autonomous cars after one of its cars hit and dragged a pedestrian due to a failure of its collision detection system. So the question I want to ask today is, how can we guarantee the reliability of the outputs of learned perception systems in new environments? And towards that, think of this modular autonomy stack that robots often have. Maybe you have some instruction, okay, go get me a fruit bowl given to the robot. The robot maybe interprets that instruction and then makes a plan using its planner to the kitchen. While doing so, it's perceiving the environment using the sensors it has on board and taking actions based on what it's seeing. And then you close the loop, and as you get more information, the robot maybe changes its plan accordingly. In this modular autonomy stack, if you have some learned off-the-shelf perception system that's, in this case, for instance, doing object detection, you can see in unfamiliar environments, you don't actually know how this learned perception system, pre-trained perception system, is going to work. So in this example, you have this quadruped that's navigating in this indoor setting. We have the ground truth bounding boxes given by these blue boxes that you see here, and then the predictions from an off-the-shelf pre-trained perception model given in red. You can see they're not exactly right, and you can see from this image, this is what the robot is seeing. There are quite a few occlusions to the chair. This chair at the back is not totally seen clearly, so that leads to perception errors. So if there are perception errors, it doesn't really matter if your down-the-stream planner is safe, because your perception errors are then going to compound into your planner, and you can get unsafe behavior. really what we want to do today is think about how we can quantify the uncertainty of learning-based perception systems. When we try to quantify the uncertainty of such, black box learned perception systems, there's usually only a heuristic, if any, notion of uncertainty. A lot of the times, the environments that we deploy these models in may be different from the training data set for robotic applications. And the robot actions, that is the closed loop behavior of the autonomous system, may actually lead to a different distribution of observations than the training distribution for your perception system. So the goal here is to use some sort of uncertainty quantification techniques to calibrate the uncertainty of any off-the-shelf perception model to get a new calibrated system. So in this case, again, the red boxes are the predictions from the off-the-shelf perception module. And we want to get a calibrated perception model, I'm calling this phi bar, such that you can have some guarantees, statistical guarantees on its correctness. And then you can use this calibrated perception model in your planning framework. I'm going to think about it in this indoor navigation setup where we have a quadruped that's navigating this office-like setting. So we want really some policy pi that uses this calibrated perception model phi bar that is safe in an unknown environment. This unknown environment is sampled from an unknown distribution of environments, and I'll get to what that means soon. And we want this policy, the end-to-end deployment of this policy, to be safe in a new environment with probability at least 1 minus epsilon. This epsilon over here is a user-chosen risk level. So you can imagine saying, okay, I want to be safe 95% of the time, and then this epsilon is 0.05. Yeah. So that's the goal. You want some end-to-end statistical assurance and safety when you're using some off-the-shelf perception model, and then also some navigation setup or some planner, safe planner. So to do this, to get this guarantee on the correctness of the perception model, we use a statistical technique. It's called conformal prediction. Conformal prediction was first proposed in about 2005, I think, but the history dates back to the mid-1990s as well, by Vladimir Vovk. And you can find out more in this book, Algorithmic Learning in a Random World. So here's the basic setup. You assume you have some pre-trained perception model, you have some pre-trained model, and you have access to a calibration data set that has IID inputs and labels. So by input, in our case, it would be observations, x1 through xn, so you have n observations, IID. And then you have the corresponding ground truth label of what's actually maybe the right bounding box output in our case, right? Compared to what the pre-trained model is outputting. We define this non-conformity score that gives us some measure of how well the pre-trained model performs compared to the ground truth label, compared to what's actually happening. And so we compute this measure of how well the model is performing over all of the samples that we have in our calibration data set. And then we can use these non-conformity scores to get a prediction set that is statistically guaranteed to be correct. So what does this non-conformity score look like for us? For us, we want to compute some notion of the perception error. Let's assume we're doing object detection and we have a bounding box outputs from our pre-trained model. I'm going to call the union of these red box predictions B, and I'm going to call the union of all of the actual locations of the objects A. We want to find an inflation for the off-the-shelf predictions for the BIs such that the ground truth is completely enclosed by this inflated bounding box prediction. You can imagine, in this case, maybe you have the length, width, and height predicted by, so you have some bounding box prediction, BI, and you want to maybe increase or inflate the length, width, and height of this bounding box by QI, such that this new inflated bounding box completely encloses the ground truth location. And you want to find really the minimum such inflation. So this is really a measure of perception error, how much you need to inflate your outputs by so that you're actually enclosing the true locations of the objects. But the score that I've showed you actually applies for a single observation from one state. And in conformal prediction, what you want to do is collect a set of all of these scores over our calibration data set. You want to arrange increasing order, and then we want to find the threshold such that we want to find this Q hat threshold such that if you apply this Q hat inflation to any prediction online, you're statistically guaranteed to be correct. And the question now is, what is really the calibration data set here, and what consists of your nonconformity scores? So the first option that you may think of is to just collect these perception errors, these inflations from all locations in an environment, and use those different perception errors from different locations in your environment, different states in your environment, and perform this calibration procedure, find this CP threshold. The nice thing about this is that this gives you a guarantee on your perception output, but this only works in one environment because now your calibration data set only consists of different locations in a single environment. Let's consider another option here where we consider many environments in our calibration data set. So we have samples of IID environments from some unknown distribution of environments. Now you collect the average perception error in each environment. So average perception error across all locations in each environment. And you use that average perception error as your nonconformity score. You arrange that nonconformity score in ascending order and find the threshold, like I showed you before, to get the inflation needed for your perception output. So now, instead of having this calibrated perception model work in just one environment, it's going to work in many different environments. So let's try that out. So here, the red boxes that you see are the calibrated predictions from your perception model. And even here, you can see actually there's a chair in the background, and the red box that it's predicting doesn't actually completely cover the chair. So there are still misdetections in this case. And then when you apply that in conjunction with, when you use that for like a planner, you can see here the free space actually expands into where there are obstacles present. And so the safe planner, because it thinks, because it misdetects the obstacles as free space due to perception errors, you see that the safe planner actually is not safe, and it has a collision with an obstacle in the environment, with a chair in the environment. So why is this happening is maybe a question you're asking. What's happening is that the distribution of states that the planner visits is not the same as the distribution of states we have in the calibration data set. So you can imagine gridding up your environment, for instance, and then collecting the perception error from each of these locations and computing the average perception error. But what happens is that the states that are actually visited by your planner are not the same. You could also imagine then potentially deploying the planner and during your calibration and collecting a set of trajectories followed by the robot, and then computing the average perception error across these different trajectories that you're collecting. What happens, unfortunately, is that when you, again, deploy the calibrated perception system online, the calibrated perception and planning system will still visit a different distribution of states than what you've observed with the off-the-shelf perception module plus planning for your calibration data set. And the last thing that happens with this method is that if you use the planner to collect your calibration data, you cannot make any changes to your planner parameters. So we call this issue the closed loop distribution shift. And unfortunately, this method that I just showed you is not robust to closed loop distribution shifts, even though it's performing conformal prediction and it's able to give you some sort of guarantee across environments. So what we do is we collect the perception errors across many different environments, but we look at the worst case perception error in each environment. So now this perception error is the maximum perception error in each of these n different environments that you have. And this then gives you a guarantee across environments, and it's robust to any state in the environment. So when you find the inflation Q hat using conformal prediction this way, and then you deploy it online, you can see that the closes all of these true locations of the object. So the perception system plus CP inflation always covers the ground truth location of the object with some probability 1 minus epsilon. I also very quickly want to make a statement on the sort of statistical guarantee we're getting here. If you collect the calibration data set just once and do this calibration offline to get this Q hat, the required inflation that you want to get, that you want to deploy online, this guarantee from conformal prediction usually just holds for the next sample from your calibration distribution. If you want to use this guarantee again and again, either you have to collect a fresh calibration data set again and again, or we actually use the data set conditional guarantee. So this probabilistic statement, I just want to point out, holds with some probability 1 minus delta. And that probabilistic statement, that distribution depends on the number of samples that you have in your calibration data set. So just to clarify exactly what kind of a statistical guarantee we're getting, you can think of it as like a double probabilistic statement. Okay, so let's deploy this robustly calibrated perception system online, and you can see now these red boxes totally enclose the objects in the environment. But you can see they're pretty large, right? So this is looking a little bit conservative. So the question now is, how can we make this inflation less conservative? And the intuition there is that since this is robust, this guarantee holds from every single state in the environment. So you can actually consider the union of free states over time, or conversely, you can think of it as the intersection of the occupied space predicted from this perception module over time. What does that mean? Say you have at time t equal to 0, the robot making an observation, and these light red boxes that you see here are the calibrated predictions from the perception module. The dark red boxes that you see here are the true locations of the objects in your environment. And then the blue space that you see here is the free space that's predicted. So you can see there's a limit. The robot actually has a limited field of view, so we account for that while we're computing the free space. We also account for possible occlusions behind these predicted obstacles, so we also account for that. At the next time step, the red boxes showed here are the predictions from the perception module. But because the guarantee that I showed you is robust to any state, both of these predictions have to necessarily be correct. And that means that the true location of the obstacles has to lie within the intersection of both of these predictions, the red box predictions. And so over time, you can imagine as you perform this filter, the free space actually grows, and then the occupied space over time gets smaller and smaller and less conservative. I want to quickly talk about the safe planner that we use here. Really, you can use any sampling-based safe planner. We're using a sampling-based planner because we discretize our state space and we use the same set of samples in calibration as well as for our safe planner. So that's how we get the robust guarantee. We use fast-marching tree star, and we account for the dynamics of the robot through system identification. And we also account for the inevitable collision set, which just means that we look at the states from which there's no control that you can apply that will not lead to a collision with the obstacle. So we're able to account for that as well. So when you deploy this calibrated perception system online, you can see that the free space grows over time. And you can see it actually grows quite till the edge of the obstacle in this case, even though you have a potentially conservative inflation because of the filtering that we're doing. And so the safety guarantee that we now have holds with probability 1 minus epsilon for a new environment sampled IID from the calibration distribution. So when you use this calibrated perception system, that's guaranteed to be correct with probability 1 minus alpha in a new environment, and you use that in conjunction with a safe planner, you actually get an end-to-end safety guarantee as well. So I want to quickly show some experiments. We validated our theoretical guarantee that we have on hardware and in simulation. So you can see in this plot here that our method, we call it PWC, perceived with confidence, is able to bound the rate of misdetections. And by misdetections, I mean whether the perception system, the output of the perception system misdetects the location of the obstacle, which means it doesn't completely enclose the location of the obstacle in any environment. So this solid blue line that you see here is the accepted level of misdetections, that's the epsilon, and you can see our method always is lower than that. Whereas other baselines, in this case, I'm just showing the perception system that's calibrated using the average perception error, the option 2 that I showed you earlier. You can see that the misdetection rate is quite high. We compared also not just the performance of the perception system and the misdetection rates, we also compared the end-to-end performance of the planning system across a couple of baselines. We used the raw output of 3D ETR. 3D ETR is a transformer-based perception model. It's pre-trained, so we just used the raw outputs of 3D ETR. We also fine-tuned 3D ETR to the kind of environments that we're interested in using a small data set of simulation environments. The third baseline that we used is conformal prediction, but without the robust perception error, as I showed you before. And we actually saw that given a user-defined safety rate of 85%, which means that the epsilon is about 0.15, PWC is guaranteed to be safe in new environments with the lowest collision rates, but also the level of misdetections that we see is guaranteed to be below this 0.15 or 15% that we have defined by the user. We tested this on a unitary Go1 quadruped across 30 different environments, and our method PWC remains safe with low misdetections in the real world as well. So I just want to very quickly show you some qualitative results that we have. You can see in this environment, both the baseline, which is the option 2 that I showed, which uses average perception error instead of the robust perception error, both of these methods are able to successfully reach the goal. And this is happening because the path to the goal is quite open. So it's quite straightforward to get to the goal. And even if there are misdetections of the obstacles in the environment, it doesn't really matter to the planner in this case. But when it does matter, when there is an obstacle in the path to the goal, and there are misdetections, that actually, unfortunately, actually leads to collisions, as you can see for the baseline here, while our method is able to account for that because of the robust guarantee that we have. And here we have a setup where the goal is occluded, as well as this chair, the red chair that you see behind, is also occluded. And our method is also able to be robust against that. So to conclude, there are many different ways to do perception, but not a lot of ways to do uncertainty quantification without making a lot of assumptions about the perception module. What we saw here is a way to get module agnostic guarantees on the perception and planning system. So this means that you can really use any off-the-shelf perception model, and you can do this calibration using conformal prediction. And then you can use it in conjunction with a safe planner and get an end-to-end statistical assurance on safety. We validated the theoretical bounds through experiments. But really the point that I want to maybe leave you with is that increasingly we're relying on learned subsystems for robotics. This gives these systems a lot of agility and a lot of adaptability, and I think that's really great. But it's important to consider closed loop safety. It's important to consider the performance of these learned systems in conjunction with other parts of your autonomy stack, especially in new and known environments. So it's important to consider safety as well, and having a sense of how well these models are going to perform in unknown environments. And with that, I'll leave you with the overview and open up for questions. I have my email up here as well.
I have one question regarding the collection of the calibration data set. So even in a single environment, how would it actually work? How do I generate the IID samples? Do I uniformly sample a random pose in the environment, then calculate my error and collect my data set like that? Or because I think I don't really understand where these guarantees hold. Do they hold only on the data support, or can we also generalize in unseen areas? I hope the background noise is not too loud.
The first option, well, it's fine. The first option that I showed in a single environment, if you randomly sampled states in your environment, if you looked at the perception error from these random samples, the guarantee is going to hold for a new random sample from the same distribution, the same way, just sample the same way. For the second and third option, you actually have this IID requirement across environments and not across states in an environment. So that's why I mentioned we need a sampling-based safe planner. So in every state, we use the same set of samples that we are going to use in our safe planner. So we fix those set of samples, and you can sample them however you want. As long as it's consistent between what you're using for your safe planner and the calibration, you should be okay. The IID-ness here is across environments. So we're assuming there's some high-dimensional, maybe unknown distribution of environments, and you have access to IID samples of those environments. So this guarantee holds in a new environment that's sampled IID from this distribution of environments, but this holds robustly in a given environment. Does that make sense?
Yes,
Great question.
Okay, so we have some question in the chat. Karthik, are you still here? Maybe you can you can also speak up, but I can also read out. So the question is related to, so first of all, the idea of characterizing uncertainty using an inflation metric is really cool. This question is related to uncertainty coverage. The first one is referring to the problem definition. By choosing to ascertain the system performance against a set of calibration data set, aren't we sacrificing the uncertainty representation? If so, is there a way to characterize the loss per se? And the second question is finally, is there some way to identify, do we have enough calibrated data?
Yeah. If I understand maybe the first question correctly, I think the question is, how are we limiting ourselves to object detection? And really, I would say some of the stuff that we want to do in the future is to generalize this to maybe occupancy maps or occupancy grids, and having a more general notion, not just like bounding box notions of uncertainty. It really depends on how if you can define your nonconformity score, the perception error, well, I think it shouldn't matter. This is just one example of how you can define this error, but really for different applications, you could do it differently. You can apply the same conformal prediction pipeline to, for example, semantic labels of human pedestrians versus bicyclists versus cars on the road to be able to get some sort of guarantee on how correct your semantic labels are, and then potentially account for that in your planning as well. So it doesn't have to be limited to using this nonconformity score. Does that answer the question, or was it slightly different?
Anushri, thanks for answering that. My question was a little more about sampling the calibrated data sets themselves. So for example, in an open-ended scenario, let's assume we have a vast environment where the machine is operating around. In that case, in order for me to set up a whole bunch of calibrated scenes would be tough. The ideal case would be, yes, I somehow sample this infinite space perfectly where everything is now well represented. But obviously that is not possible. So I'm wondering, is there like some balance about, okay, I only need these many calibration data sets for this vast or a complex scene that I care about, that I have in front of me? That is my first question. And the second question is, like just in terms of representation, how would I know that I am actually doing this well? Like some kind of a loss metric that can represent, okay, I am reasonably doing well in these scenarios, and so that'll be some percentage. So naively, it's like a percentage representation. That is where my headspace is right now.
Okay, yeah. Let me bring back the calibration. I think you really hit the nail on the head with the first point, which is we are given these samples in every environment. So this really works for indoor navigation setups and not like open environment. And the second thing is, I think, the question of how much data is enough. Is that right? In our calibration, we do this offline, and that gives us some sort of there's a double probabilistic statement that I don't have written out here, but there is, this statement holds with some probability that's given by a beta distribution whose parameters depend on the number of samples you have in a data set. So really what happens is, if you have, in our case, 400 different environments where you're performing calibration over, we want this probabilistic statement to hold for an epsilon of 85%, or 1 minus epsilon of 85%. We know that if we want this probabilistic statement to hold with probability 0.99, then we actually need to change this epsilon to a new epsilon hat, such that quantile of 0.99 holds. So what you end up having here is like a 0.87 or 80%. Does that answer your question? And this is going to hold in a new environment with with at least 85% probability. That's a theoretical guarantee that holds
That's
even
pretty cool.
across the
I think,
validations that we have in
yeah,
experience.
that's really cool. I haven't really heard of the double probabilistic estimation before, but it's a really cool idea. Thank you.
Because I've seen that you also had a paper on adaptive conformal prediction. How easy would it be to just replace this with the adaptive version? Because then we wouldn't really need to collect a calibration data set anymore, right?
You do, I mean, in the adaptive version, what we had is we had like a dynamically moving obstacle, and we assumed that we knew afterwards the exact trajectory that the obstacle had taken. And so we were actually getting a fresh calibration data set of the last n time steps and using that every time. But the adaptive conformal guarantee is slightly weaker than this one, because this statement then holds on average in that case, which is why it's not what we use here. And that one, I think, was designed for like a single environment. So it's closer to option one that I showed, for instance. And this holds across new environments as well. And is but if you had, say, this is, again, an instance where you have static objects, right? But in the case of dynamically moving objects, or if you have interactions with humans, for instance, you can imagine that over time, maybe the human's going to adapt to the robot behavior as well. And the calibration data set doesn't really reflect what's happening in the real world or in the interaction anymore. And then you can imagine having a slightly more adaptive approach. So that's what you lose with that adaptive approach, is that you get that this statement holds, this probabilistic statement holds on average. Yeah.
Okay, thank you.
So if you were to use this for like manipulators, and you want to also consider like the dynamics of the whole system, and do you think, and also with the vision integration, where you would really need to compute all of that in a, for example, at least 200, 300 hertz, if not 1 kilohertz, is this scalable to that kind of a setup, or what are the challenges, do you think?
I mean, this setup is, it really, the inference time here depends on the inference time of your off-the-shelf like object detection module, because you do all of the calibration offline. You get this prediction, like how much you need to inflate it by offline, and you can just add that number to your prediction, and that just works. So all of the computation, it's very lightweight, and all of that computation is happening offline during your calibration. For manipulation examples, you can imagine maybe you have like a grasping setup where you're trying to figure out where the object, and maybe you have like an area where you could, a patch where you could grasp it. You could imagine doing a similar sort of uncertainty quantification where you shrink it, where you have a smaller patch that's guaranteed to be correct, and then you can have like a grasping example as well. Yeah. Some other examples actually maybe kind of unrelated to manipulation that we've thought of is even like stepping stones, which is similar to this grasping example, where you want to figure out where you want to place, where the quadruped should place its feet. And if you have, again, a similar, like, oh, this is a patch where it's safe to put 1 feet, then you could, again, do some sort of calibration and uncertainty quantification to get guarantees on the correctness of that output as well.
Yeah, I think that answers my question. Thanks.
So I think Riddhiman brought about the manipulation example. So I had a question about how you would quantify uncertainty in a traditional object detection system where you are getting a bounding box along with the label. So in my experience, the errors or the issues with the such sort of object detection systems is that you probably don't detect the object at all. You don't get the bounding box or the label, or you get the bounding box but a different label, or for the same object you get multiple bounding boxes and multiple different levels. So how can this system take care of those sort of things?
Yes. So actually 3D-TR, the perception system that we use, gives us semantic labels. It gives us some confidence scores on the objectness probability, as well as what was the last one? I think I'm missing one.
Yeah, so it's for the same object. Sometimes you get
Yes.
different labels and like bounding
That
boxes
happens
so
as
that,
well. I mean, it tries to suppress this intersection over union, the IOU loss.
yeah.
Um,
Okay.
happens. And so what we really did was, and that's where inflation becomes conservative. So you don't know how many objects there are going to be in your environment. You could take, if you knew at most there were 5 objects, you could take sometimes the top 5 most confident predictions didn't even the true didn't even have like predictions of true locations, right? So in those cases, then the inflation gets higher because if you're far off, then that inflation is going to grow. So it's trade-off. I mean, we predicted about like 15 bounding boxes in every environment within our field of view. Most of the time they were super noisy and they would be just outside of our field of view, which would be occupied or unknown anyway. But that filter that we have that computes the intersection over time really quickly gets rid of the noise, which is nice for us. And so just to give you some numbers so that you have some sense of like what that inflation, we were making like 15 bounding box predictions at every time step. We were inflating those with the robust guarantee by about 0.7 meters, the length, width, and height on each side. As opposed to the second option that uses the CP average, that inflation was 0.05 meters. So there's a huge difference. So the intersection, the filter, the non-deterministic filter is what we call it, really helps in that case to get rid of the noise. Another thing that we were doing, and this is more of the dirty laundry, I would say, is we were computing the IOU loss of the predictions, the bounding box predictions. So if there was a lot of intersection, like there were a lot of boxes predicted at the same location, we would just use the most confident prediction, the prediction with the highest label. So we had a threshold, but we were consistent about that in our calibration as well as when we implemented it online. So the guarantee still holds that it's not an issue. But we're thinking actually about different sorts of non-conformity scores. You can imagine you don't actually have to have like an inflation that's defined like this. You could have a multiplicative inflation where you're maybe multiplying the length, width, and height by this threshold Q. So you're finding that inflation. And that would depend on the size of the bounding boxes. So you're not inflating really small bounding boxes by 0.7 meters as well. You could have something that depends on the size. You could potentially account for the confidence scores that you're getting from your object detection module and multiply those then as well if you want. So we're actually thinking about what are some different non-conformity scores which will give us potentially even better results. And using maybe different perception modules, maybe those work better. We're open to doing all of those things.
Thank you. Just a quick follow-up question. So are you, is it incorporating sensor noise or the errors due to sensor noise? Because RGBD cameras, they essentially have like a range of operation where if you are too close to the camera or if you're beyond a certain range, you have more sensor noise. So is that being incorporated or is there any way to take into that account as well? So.
Yes, so we're trying to, in simulation during calibration, be as close to the sensor model as possible. This means that we have the same range. It was 1 to 5 meter range. So it performs actually pretty well, I would say, in that range. We know from the camera data sheet about like the perception errors that we can get in those situations. So we are able to account for sensor uncertainty as well as what we really account for. We didn't see as much sensor uncertainty, but what we really accounted for is state uncertainty. Like we did SysID to get some notion of like what the dynamics are, but if there's some error in that, we were able to account for that. The inevitable collision set that I briefly mentioned. Yeah.
Okay. Thank you.
Yeah, there's one question in the chat from Sanya who says that can this method be also scaled to autonomous vehicles for obstacle avoidance?
Yeah, I mean, I started out with that example and I didn't quite go back to that example. So it's a great question. Right now, this works for static obstacles, and it would be really interesting to extend this to dynamically moving obstacles, which is often how you see autonomous driving scenarios. That's where I think that semantic classification of what kind of objects are in your environment and labeling that and getting some sort of confidence estimates of that might be useful. And then you can robustify against whether maybe there's a bicyclist in the environment, or maybe there's a pedestrian, and then maybe you can account potentially for both if you're unsure which of them it is. Or if you're confident that it's a bicyclist, then you account for that motion.
Thank you first for the great talk, and I would ask you if we wanted to have a different epsilon, so a different bound on our confidence on the error. Should we train the optimization again, or we can rely on, for example, this graph that I see on the scores in the slides that you had before to compute online?
Yeah, great question. No, you don't have to redo all of this. If you have the perception errors, the worst perception errors or the average perception error, really it's about, oh, let me get that picture up here. Yeah. So it's about, if you have these scores, which you need to compute really only once, the skew hat, the threshold based on the confidence that you want, just moves in terms of like where this line is, right? So you can do that very quickly. You don't have to redo the calibration if you've already collected the perception errors and the non-conformity.
Yes, thank you. That's brilliant. And can I ask you another thing? Since now it's really in vogue, generative models. So, how do you think, to create a generative model of what is the error, let's say? So, like a distribution of probability of where is like the true box, given like a data set where you have the
That's a great
prediction,
question.
and maybe it's much more data hungry, or what are your thoughts?
Yeah, that's a great question. I mean, yeah, it's okay if it's data hungry because it's offline. The calibration happens offline, so I'm not too worried about that. But that's great. I think maybe it depends on how you define this non-conformity score, right? Like, that's interesting. I don't know. Maybe you want to have, I'm just thinking out loud here, so I could be like totally wrong. Maybe you could have like a non-conformity score that's defined by some heuristic notion of uncertainty in your predictions, and that what do you think of that? I think it depends. Again, really, it depends on how you design that non-conformity score.
Yes, indeed, it's also really interesting what you said about the probabilities. In fact, I want to check out the paper to go in details on that. And yes, anyway, really a great approach. I find it really elegant and simple. But I was thinking about this generative because now it's really a big trend. And I was thinking that indeed, somehow you are measuring the performance of the estimator with this box. So I was thinking because a generative model would also give you a probability of the error. So for example, it can tell me how, with this probability, then I can be more aggressive or less aggressive, going close to the object.
Yeah, I mean, you can adjust that through using these non-conformity scores.
Just one quick comment from Karthik. I just want to read out loud. I think it would be bounded by the epsilon, considering the calibration data sets a subset of the open set.
What would be bounded by the epsilon?
Sorry, I was commenting on the previous gentleman's comment about how it would work on a generative distribution. And my thought was, because the calibration data sets have to be a subset of the generative distribution, so the epsilon would still be applicable in this case, although it will not be purely the epsilon, but it'll be a scale factor of the epsilon based on the generalizability of that distribution. I think there is some vagueness to that, but the key idea is the calibration data sets being a part of the generative distribution, or whatever that is, that bigger open set. I think based on that thought, the epsilon would still carry forward in some way or form. That was my thought. But again, I think it's a really cool idea. Thanks for sharing it.
Yeah, I think we are almost exceeded the time, but it was a very nice discussion. I think this was after a long time we had such a big discussion and nice interaction. I want to thank Anushri again. Thank you for the time. Thank you for showing us this new perspective, and all the best to you in the new role. And hopefully we see each other in some conferences somewhere. Great to have you.
Yeah,
Thanks.
absolutely. Thank you for having me. This is a lot of fun.